The purpose of this video is to introduce you to the concept of similar polygons, to introduce you to some properties that accompany similar polygons, and to use those properties in solving problems that involve similar polygons. Now we say that two figures are similar if and only if they have exactly the same shape, but not necessarily the same size. When two polygons are similar, some really interesting things start to happen. First of all, corresponding angles are congruent. And it's important to note here that the angles that we're talking about are always the corresponding angles. And we'll talk more about that later in the presentation. Lengths of corresponding sides are always going to be proportional. And again, in order for that proportion to exist, those sides have to be corresponding. That's really, really, really important. Just like a lot of other ideas in geometry, we have a special symbol to represent the word similarity. So the symbol that we're going to use when two items or two polygons are similar is that little squiggle. When we see that little squiggle, the word that we're going to think is similarity. Now let's take these two quadrilaterals, ABCD and EFGH. They tell us that quadrilateral ABCD is similar to EFGH, or in other words, written symbolically, ABCD and then the little squiggle, EFGH. Now as far as what it means for two things to be corresponding, it means the same thing as it did back when we talked about congruent triangles. Angle A would correspond to angle E. Likewise, angle B would correspond to angle F, so on and so forth, all the way around the polygon. So those would be the pairs of angles that would be congruent to each other. So if I wanted to go list my pairs of congruent angles, angle A would be congruent to angle E. Angle B would be corresponding to and thus congruent to angle F. Angle C would correspond and be congruent to angle G. And lastly, angle D would correspond to and be congruent to angle H. Now, similar to the angles, but not quite the same, the pairs of corresponding sides would be in proportion. So if we go back and take a look at our picture and take a look at some pairs of sides that would be considered corresponding sides, side AB would correspond to side EF, side BC would correspond to side FG, side CD would correspond to side HG, and then lastly, side AD would correspond to EH. And while these sides obviously aren't congruent because one quadrilateral is bigger than the other, because these two figures are similar, we do know that the lengths of their corresponding sides are in proportion. So if we take and compare the length of AB to the length of segment EF, that would be the same as if we were to compare the length of side BC with the length of its corresponding side FG, which would be the same as if we were to compare side CD with its corresponding side, GH. And lastly, that would be the same as the comparison between AD and its corresponding side, EH. So big concept, corresponding angles are congruent, corresponding sides are in proportion. Now, some more vocabulary here. Anytime two polygons are similar, the lengths of any two corresponding sides is called either the scale factor or the constant of proportionality. Now what this means is you really have three terms that you need to know mean exactly the same thing. So the ratio of the lengths of two corresponding sides is the same as the scale factor, which is the same as the constant of proportionality. All right, so there's a little background. That's the nuts and bolts of what you need to know for this particular lesson. Let's go see how this applies to some problems in geometry. Oh, here we go. Just like we said, ratio is the same as the scale factor, is the same of constant of proportionality. All right, now let's go look at some examples. So if we're given that these two triangles are similar to each other, we know automatically that their corresponding sides have to be in proportion. I'm just going to go ahead and label the corresponding sides in my picture so that I have a little bit clearer idea exactly which are the pieces or the parts that correspond to each other. All right, these last two sides I want to make purple. So they're asking me in this problem to find the constant or proportionality, or in other words, the scale factor, or another name for that, the ratio between pairs of corresponding sides. So I'm simply going to pick any pair of corresponding sides. Maybe I'll pick my yellow pair, and the ratio between those two sides is 22 to 11. If I had wanted to pick the blue sides, the ratio would be 14 to 7. The ratio between the pink sides, 16 to 8. And you can see that no matter which two sides I pick, when written in simplest form, the ratio between that pair of sides, 2 to 1. All right, I'm going to go ahead and flip my paper over and take a look at that problem up at the top of the next page. It says I've got a quadrilateral who has sides of length 8, 10, 12, and 15. It wants me to find the lengths of the smallest and the largest sides of a similar quadrilateral if the constant of proportionality in going from the smaller to the larger is 2 to 5. So I'm going to go ahead and I'm going to draw a picture of that original quadrilateral just so I'll have a visual idea of what I'm looking at here. And it's not the best picture in the world, but it's going to suit my needs and purposes just fine. So I'm going to go ahead and label the lengths of the four sides. And in the problem here, they tell me that this new quadrilateral that I'm looking at is larger than the original. I'm going to go ahead and draw one that's a little bit bigger. And it wants me to find the lengths of the smallest side. Well, I know that the smallest side in my larger quadrilateral is going to correspond to the smallest side in my original. So the smallest side of my original was 8. The smallest side in my new one, I'm just going to call x. They tell me that this constant of proportionality, or in other words, the ratio, that's a fancy way of saying that the ratio between the sides is 2 to 5. So if I go compare the two sides, I get 2 to 5. Well, let's go compare a pair of corresponding sides, as 8 is to x. Notice that in my first ratio, the length of the smaller was over the length of the larger. So when I went to write my second ratio, in order to keep consistent, I had to put the length of the smaller over the length of the larger. So now cross multiplying here, I find that 2 x's are equal to 40, and each x is equal to 20. Therefore, the length of that smaller side must be equal to 20. The other thing that it wanted me to do in this problem is it wanted me to find the length of the largest side. Well, the length of the largest side in this new polygon is going to correspond to the length of the largest side in my original polygon. And since the length of the largest side in my original polygon was 15, those two blue pieces are therefore going to correspond. So I'm going to let y be the length of my longest side in my new polygon. And again, I'm going to go write that proportion. So 2 to 5 is the ratio between my sides. That's the same as 15 is to y. So if I cross multiply, 2 y's are equal to 75. Each y is equal to 37.5, making the length of my largest side 37.5. All right, number 3 is very similar to number 2, except instead of dealing with quadrilaterals, I'm dealing with triangles. However, I'm still dealing with a pair of polygons that are similar to each other. So I'm going to go ahead and again draw a picture so that I have a visual of exactly what this should look like. So there's triangle HAT. It tells me that the distance between points H and A is 9, the distance between points A and T is 15, and the distance between points T and H is 18. So again, not a very good picture, but it'll get the job done. Now my new triangle, or my similar triangle, is triangle PIN. And I can't help but notice that vertex H has to correspond to vertex P, vertex A has to correspond to vertex I, and lastly that vertex T corresponds to vertex N. In that new triangle, the distance between points P and I is 12. It wants me to find the distance between points I and N and between points N and P. So once again, I'm going to set about or start this out by comparing some lengths of corresponding sides. So 9 corresponds to 12. That ratio is going to be exactly the same as the ratio I get when I compare 15 to its corresponding side, IN. And since in my first ratio, I put the smallest side on top and the longest side on bottom, in my second ratio, I have to do exactly the same. Smallest on top, longer on bottom. I'm going to show you a little trick here. This ratio 9 to 12, I could go ahead and cross multiply and I would get a very acceptable answer, but I notice that that's not in simplest form. So before we go any further, I'm going to simplify that. And what that will accomplish for me is it'll make the computations now that I do a little bit simpler. So 3 times the length of IN is equal to 4 times 15, which is 60. And that makes the distance between points I and N 20. If I go about setting up a similar problem for the last pair of remaining sides, 18 corresponds to and compares to this distance PN. So again, I'm going to do large 9 over its corresponding side 12 equals 18 over its corresponding side PN. Once again, I'm going to reduce or simplify this guy just to make the math a little bit easier. So 3 times the length of PN is equal to 4 times 18. 4 times 18 is 72. So the distance between points P and N, 24. All right, the next one is a little bit different in that they're not asking us to find the lengths of sides, but rather they're giving us the lengths of the sides, and they're asking us to determine whether or not the two polygons below are similar. So in other words, are their corresponding sides in proportion? In order to do this problem, I need to make sure that I am consistent in my comparisons. For instance, when I compare the smallest side of this little triangle to the big triangle, I need to make sure I compare smallest side to smallest side. So looking at the 3 sides of this larger triangle, 27 is the smallest side, so I'm going to compare 15 to 27. I'm going to compare the longest side of the first triangle with the longest side of the second triangle. And likewise, I'm going to compare the middle 2 sides of each also. So if I find that those 3 ratios that I get when I compare are equal, I'll know that my triangles are similar. So if I compare smallest to smallest, I'm going to compare 15 to 27. I want to know, is that equal to the ratio that I get when I compare the middle 2 sides, 20 to 40? And is that equal to the ratio that I get when I compare the longest 2 sides, 25 to 45? Well, in looking at this comparison, quite clearly, all of those don't simplify or reduce to 1/2, so this has to be a definite no. All right, the last one gives me a couple pentagons, and it wants me to find the lengths of the new pentagon after telling me that the 2 figures are similar. So starting out with a couple similar figures, I know then that the lengths of their corresponding sides have to be in proportion. So if I go ahead and do some comparison, side FE or SE is going to have to be compared to side ty. Well, looking at that, I can tell quite simply that the scale factor here, or the constant of proportionality, or the ratio between the sides, is going to have to be 4 to 2, or in other words, 2 to 1. So everybody in the larger pentagon is going to be double the length of its corresponding side in the smaller pentagon. So what that means here is if this piece is 4, this guy has to be 2. Because this guy is 6, he has to be double the length of the smaller one, making the length of OD 3. The length of this guy is 3. AD has to be exactly half of that, or 1.5. And then lastly, if this guy here measures 6, its corresponding side over here is going to have to be half of that. Oops. Or in other words, 3. Excellent. Now, if you had any questions while watching this video, I want you to jot them down right now so that you can remember to ask when you come back to class. And if you do have questions, of course, we'll address those when you come back to class, as well as work on some practice problems involving similar polygons.